Hi, my name is Zi Yun from Cornell University. I'm working with Professor Emmanuel Charmer. Today, I'm very happy to share our recent work on applying parallelization to adaptive query processing. In this paper, we're trying to figure out the balance between plan searching and query execution by multithreads for the purpose of the plan efficiency and robustness. In database systems, Query Optimizer plays an essential role in deciding how to execute a query in an efficient way. Finding a good query plan can significantly save query execution time. The optimizer relies on cardinality estimation and empirical cost models. It's easier to find an optimal query plan with a more precise estimation. However, making correct estimations is very challenging. Sometimes the estimated value can be several orders of magnitude away from the true value. To estimate cardinality reasonably, traditional query optimizers select the query plans based on data statistics like min-max or histograms. Furthermore, they rely on simplified assumptions to estimate cardinality. Then query optimizers estimate the cost of plan candidates based on cardinality estimation and search for the optimal plan using dynamic programming. After having an optimal query plan, the execution engine fetches the tables and performs operators in the order that query plan suggests. Traditional query processing has several challenges. Obviously, the collected statistics are too coarse-grained, losing the information to represent the whole tables. Also, simplified assumptions may not hold for many realistic databases. Nowadays, researchers work on learning and re-optimizing the query adaptively. The main goal behind this strategy is to rely on minimum assumptions of data in a query and provide a formal guarantee of expected performance. Essentially, the adaptive query processing attempts to try out different query plans during the execution. As soon as a better plan comes to light, the execution engine seamlessly transitions to a more efficient way to execute the query. Here's a typical procedure of adaptive query processing. Initially, it selects a query plan from the search space. Then, the selected plan is executed over a short time slice. When finishing the join phase, the reward of the plan is updated back to the search space and completes a learning episode. After this step, the procedure jumps back to the step 1 to learn from another query plan. Adaptive query processing is effective for finding a good query plan with a decent bound of expected optimality, but it still has some challenges, especially when the query and data are relatively large. Think about this example. The search space of the query plans is quite large, but executing any of the plans is comparably cheap in addition to the most optimal one. Based on the learning algorithm, in the worst case, the optimal query plan can be the last one to evaluate due to the random exploration, which makes the learning phase the main bottleneck. On the other hand, if the optimal plan happens to be selected very early, the learning algorithm may stick to this plan before the query execution is done. Due to this randomness, the time for plan convergence can have a large variance. Given an optimal query plan, when the data size is pretty large, the execution of the queries can become the primary overhead. To overcome both challenges, the straightforward approach uses multiple threads to parallelize both phases. In this paper, we're trying to address challenges by using the multithreading. Eventually, we want to show that our multithreading design choices can improve the performance and robustness for adaptive query processing. In current computer systems, multi-cores are widely used for generic purpose of the performance acceleration. It increases the degree of the parallelism by multithreading, and threads communicate with each other through the shared memory. For traditional parallel query processing, the optimization part is efficient, so multithreading is mainly applied to the query execution. For each operator, the parallel version of the operators needs to be implemented into the database systems. The parallel design of adaptive query processing, however, is not clear to us. In high-level ideas, we probably want to parallelize the plan selection or the query execution, but we're still curious about how to adapt each parallel design for different learning scenarios. In this slide, we're going to illustrate our design choices for adaptive query processing on multi-core platforms. Considering a two-dimensional partition choice, where the x-axis represents a unique combination of the table partitions, and y-axis represents a subset of the query plans in search space. When the search space is quite large, finding the optimal plan among plenty of the candidates is not that efficient. So we want to partition the search space. Here we can see that y-axis is partitioned by different colors of the threads, and each thread covers all table partitions on x-axis. With a smaller search partition, fewer query plans will be explored, reducing the time to achieve the convergence of optimal query plan. This is helpful to save time spent on bad plans and more likely to find the optimal query plan before completing the query execution. However, threads working on search partitions cannot share progress with each other, which means that executing a query plan is still single-threaded. When considering the trade-off between the learning convergence and plan execution, the search parallel locates at the right bottom of the figure. The second challenge can be resolved by executing data partitions in parallel. As shown in the figure, different threads take over data partitions and learn the optimal query plan of the entire search space. This method accelerates the execution phase, but may have trouble finding the optimal plan efficiently. Then we're trying to figure out whether there's a hybrid method to resolve both challenges by combining these two parallel strategies. As an example here, we have 3 data threads working on the same search space but different data partitions, while the orange and purple threads explore different search spaces on full data. This diagram illustrates the fundamental aspects of the Skinner-MT system, where our primary focus lies in optimizing the join orders. The input query is transformed into SPJ queries in the first step, and then the unary predicates can be pushed down to filter base tables as pre-processing. After that, in-memory hash indexes are created on columns that appear in equality joins. On the right-hand side, Skinner-MT employs adaptive processing strategies to learn and execute queries. The learning optimizer uses a reinforcement learning algorithm. In each learning episode, it selects a join order and performs a specialized Montewi join algorithm to evaluate the reward. In a parallel setting, Skinner-MT integrates a coordinator that controls the working thread for searching plans or executing queries in parallel. The execution states are maintained by a customized data structure called progress tracker. In the following slides, we want to describe each parallel method in detail and briefly introduce our progress tracker and experimental results. We start with data parallelization. The traditional join algorithm joins 2 tables each time, causing a large intermediate result and hard to keep progress when the join order switches. So Skinner-MT uses a customized Montewi join algorithm. As shown in the graph below, the algorithm finds the next satisfied tuple in the current table. Once the tuple is satisfied with all of the predicates, it will proceed to the next table. This algorithm generates complex join result tuples as quickly as possible and never keeps more than one intermediate result tuple at one time. At the beginning and end of the join, the execution state will be restored and updated to the progress tracker for the later use. The parallel version extends the Montewi join algorithm by choosing one table to split. For the split table, it extends the jump procedure by checking whether the tuple still belongs to the thread. We could add an additional predicate to restrict the thread scope. However, we find that choosing a split table is important and sometimes not trivial. And here's an example. By choosing the different split tables, the slowest thread needs a different number of the steps to finish the join. For the best case, when splitting the table T, the red thread takes 8 steps, but when selecting table S, the green and blue threads both take 11 steps, which is 1.4 times more steps. To solve the data skew problem, we put forward a cost model for split table selection, since the cost of the parallelization is determined by the slowest thread. The goal is to minimize the maximal per thread cost. First, we collect the statistics from all threads, which represent the percentage of the tuples covered in each table during the last learning episode. Then, we estimate the remaining cost for a given split table by deriving an upper bound and lower bound for the given split table. The split table can be changed only when the slowest thread decides to partition another table. As an alternative, we introduce the search parallelization, exploring more join orders in parallel. This can be helpful if good join orders are very hard to find. Each worker is assigned to a search space partition, learning and executing the optimal join order according to the reinforceable learning algorithm. Here, we consider two variants of the search parallelization, and the first but naive one is partition the search space uniformly. This means that each thread searches a space of the same size by fixing the join order prefix. Whenever a thread finishes a query execution with a global optimal join order, it broadcasts the termination signal to other threads. An improved version starts with a uniform search space partitioning, but adaptively changes the assignment of threads to search space partitions. Ideally, the number of the search threads per partition is proportional to the average rewards observed in each partition. By doing this, we don't have to waste the threads working on inferior partitions. After discussing about data and search parallelization, we are more interested in combining both ideas into a hybrid parallelization algorithm. We think about the learning instance. At the beginning, the algorithm explores join orders and learns which join order is the most optimal one. With more learning episodes, the optimal join order gradually converges, and query execution sticks to this join order for the rest of time. Based on this intuition, we divide threads into two groups, search threads and data threads. The framework is like a producer and a consumer. Whenever the search threads find a new optimal join order, it will be sent to the data threads and execute on data partitions. Similarly, we also consider two variants. In the simple case, the number of the search and data threads remains fixed, while the second version gradually transitions from the parallel search to parallel data over the course of the query execution. This design aligns more closely with the inside principles of learning. Finally, we briefly describe our progress tracker, which maintains the execution state of multi-way join algorithm. The execution state is captured by one integer number per table. This number indicates the position of the current selected tuple. The join orders are represented as nodes in the progress tracker tree. When restoring and updating the execution states, we start from the node of the first table and traverse the edges associated with the rest of the tables in the join order. We read the tuple index from each node along with the traversing path and override the existing progress at the end of the join procedure. We were running our experiments on Ubuntu 20.04 with 24-core server, and the total DRAM is 252 gigabytes. We evaluated 3 benchmarks. Here, we only show the GLB benchmark, and the rest of the results have the same tendency. The first experiment shows the time speedup and the variance for different parallel methods. In the left figure, the search parallel shows a very low speedup, while the hybrid parallel method can achieve more than 9 times speedup. It indicates that the data parallel is more important in terms of the performance improvement. On the right-hand side, we run queries 10 times and report the ratio of the maximum to minimum running time. The search parallel always provides a robust query plan, which only has around a time ratio of 2. And then we compare end-to-end performance for different existing database systems, including Postgres and MongoDB. Obviously, on the join order benchmark, our system achieves over 6 times end-to-end speedup compared to a single thread and outperforms MongoDB by running 2.3 times faster. Lastly, we want to quantify how good our join order is by injecting the last selected join order into the Postgres execution engine. We compare our system with other learning query optimizers, such as BAO and AQO. We ran the GLB queries in the original order, inverse order, and random order. In our method, the selected join order has comparable quality as a BAO inverse, but outperforms the original BAO by 1.2 times speedup. To conclude, we explore design choices by applying the parallelization to adaptive query processing. More specifically, we propose search parallelization, data parallelization, and a hybrid method to balance the search parallel and data parallel. We integrate all parallelization methods into our system Skinner MT and achieve around 10 times speedup compared with the Skinner DB and also higher scalability than MongoDB. Thank you.